Good afternoon, everyone. My name is Zixuan Wang. I'm from Shanghai Jiao University. Today, I'm glad to present our research paper, One-Sided Memory Window, a system for managing disaggregated memory efficiently, flexibly, and securely using RNIC offloading. So let me start with some background on the disaggregated memory architecture, or DM architecture. So the key idea of disaggregated memory is to separate compute and memory resources into two independent hardware pools connected over a network. In this work, we mainly focus on RDMA-based systems. In DM architecture, compute nodes typically have strong CPUs but limited local memory. Memory nodes have abundant DRAM but very weak or even no CPU power. Compute nodes can access remote memory through one-sided RDMA, which gives us a microsecond level latency. Now, in the DM architecture, how to managing disaggregated memory is a critical problem. The disaggregated memory management by the memory node have to handle allocation and deallocation requests from compute nodes, and at the same time ensure memory isolation, which means that a compute node should not be able to access memory belonging to other compute nodes. So the key challenge here is a trade-off. Fine-grained allocation improves memory utilization, but introduces high overhead on the memory node's weak CPU. So let's look at how existing approaches handle this problem. The first approach is what we call static MR, which relies on RDMA memory registration, which is a time-consuming and CPU-intensive operation. So static MR avoids registering memory regions on demand. Instead, it pre-registers memory in large and coarse granularity to minimize memory node CPU overhead. When a compute node needs more remote memory, the memory node simply allocates from these pre-registered regions. This approach is adopted by most systems like fast swap. The main advantage of static MR is that it only requires minimal memory node CPU involvement, and the memory access is ultra-fast using native one-sided RDMA. However, because it allocates memory in coarse granularity, it causes severe internal fragmentation and poor remote memory utilization. The second approach is what we call RPC memory window. It relies on a lightweight protection mechanism in RDMA called memory window. A memory window can be bound to a very small part of a pre-registered memory region. The binding operation is extremely fast. It takes only microseconds and can be performed in user space. Systems like Petronas use this approach, where compute nodes send memory allocation requests to the memory node using RPC, and the memory node performs memory window binding on demand to serve each request. RPC memory window can improve memory utilization because it's fine-grained allocation, and the memory access is still fast using one-sided RDMA. However, since every allocation and deallocation request requires an RPC, which will involve the memory node CPU, and the memory node CPU is weak, when it gets overwhelmed, performance degrades severely. The third approach is ODRP. ODRP is a kernel swap-based disaggregated memory system that offloads all swap and paging logic to the memory node's RNIC. To be specific, the memory node divides its memory into 4 KB pages and offloads all access and management logic to the RNIC via work request chains. When a compute node sends a swap request, the RNIC executes the offloaded logic directly on the memory node's RNIC. ODRP achieves no memory node involvement and optimal memory utilization through page-level allocation. However, ODRP has two significant limitations. First, every memory access must go through address translation implemented in the offloaded work request chain, which will introduce additional latency compared to one-sided RDMA. Second, ODRP only supports fixed 4 KB access granularity, which limits its applicability. So to summarize the problem, none of the existing approaches achieves all the following design goals simultaneously: high memory utilization, no memory node CPU involvement, high performance, and flexible I/O size. So our key insight is we can retrofit RNIC offloading to perform memory window binding and unbinding operations remotely. This enables fine-grained on-demand memory allocation with zero memory node CPU involvement. Based on this insight, we propose a system called one-sided memory window, which has the following design goals: no memory node CPU involvement, high memory utilization, and high allocation performance and high access performance, and strong memory isolation and supports arbitrary I/O sizes. Before diving into the detailed design, let me quickly recap how RNIC offloading works. RDMA communication is based on queue pairs or QPs. Each QP has a pair of send queue and receive queue. RNIC offloading is enabled by a special work request called wait, which basically suspends the RNIC's execution on the send queue until an incoming RDMA send request arrives. The incoming send request triggers a pre-programmed work request chain to execute entirely on the RNIC, no CPU involved. The work request chains are composed of basic RDMA operations like read-write, atomic fetch-add, and atomic compare and swap. They can express complex logic, and actually they are proven to be Turing-complete by written paper at NSDI 2022. Now let me walk through the one-sided memory window design step by step. First, the memory node organizes its memory into fixed-size chunks with a configurable granularity. Second, for each memory chunk, the memory node pre-allocates an initially unbound memory window. Third, the memory node maintains a memory window table that stores the metadata for all memory windows, including the base address of each memory chunk and the R key of its corresponding memory window. Fourth, the memory node uses a free memory window queue to track all available memory chunks. Each queue entry contains the address of a memory window table record. This free memory window queue is implemented using a ring buffer with a head pointer and tail pointer. Finally, and the most importantly, the memory node offloads work request chains to its RNIC. These work request chains implement the allocation and deallocation logic without involving the CPU. Now let me introduce the workflow of serving a remote memory allocation request from a compute node. When a compute node needs more remote memory, it sends an allocation request, which is basically an RDMA send operation with argument to the memory node. This incoming send operation triggers the RNIC, the memory node's RNIC, to execute the pre-offloaded work request chain. The work request chain first dequeues a free memory window table entry from the free memory window queue using an RDMA atomic fetch and add operation on the queue head pointer. Then the work request chain uses the metadata in the allocated memory window table entry to bind the memory window to its corresponding memory chunk. Finally, the work request chain writes the memory chunk metadata, including the base address and the memory window's R key, back to the compute node using an RDMA write, one-sided RDMA write. The entire process happens on RNIC with no memory node CPU involvement. After that, the compute node can directly access the allocated memory chunk using one-sided RDMA with the returned R key. So far, I haven't mentioned one important design choice in one-sided memory window. There are actually two types of memory windows, type 1 and type 2, each with different properties and trade-offs. Now let me explain why we choose type 2 memory window over type 1 by walking through the security problem with type 1 memory windows. So with type 1 memory window, after the memory window binding operation, any QP can access the memory area as long as it provides the correct R key. This is simplifying, but there is a fundamental vulnerability. When a type 1 memory window is rebound and reallocated to a new compute node, only the lower 8 bits of the R key change. The upper 24 bits remain the same because the RNIC uses these bits to index the memory window's on-chip metadata. So a malicious node can simply enumerate all 256 possible R keys to gain unauthorized access to memory that has been reallocated to another compute node. This is a serious security vulnerability. To avoid this problem, we must use type 2 memory window for strong isolation. So type 2 memory window can provide strong isolation through a property called exclusive assignment. After the memory window binding operation, the type 2 memory window is exclusive assigned to the QP that performed the binding operation. Only this specific QP can access the memory area or unbind the memory window. Any access attempt from other QPs will be rejected by the RNIC hardware. This gives us strong hardware-enforced isolation. However, this strong isolation comes at cost. A compute node typically establishes multiple QP connections for two reasons. First, multiple QP can fully utilize the RNIC's internal parallelism to improve the performance of concurrent memory access. Second, requests can be routed to different QPs to prevent interference. For example, in a swap-based system, latency-sensitive swapping requests should not be delayed by latency-insensitive page prefetch request, right? However, the exclusive assignment property of type 2 memory window conflicts with this model QP setup, creating two performance challenges. The first challenge is what we call performance interference within a QP. Because the type 2 memory window can only be accessed via the QP that originally performed the binding operation, all access requests targeting the same memory chunk must go through the same single QP. This means latency-sensitive requests can be delayed by latency-insensitive ones when they happen to access the same chunk. The second challenge is offloading overhead with multiple QPs. Because type 2 memory window require each QP to independently perform memory window binding operation. So each QP needs its own offloaded logic. However, we discovered and confirmed with NVIDIA engineers that having too many QPs with offloaded logic actually can degrade the performance of one-sided RDMA. With 96 QPs with offloaded logic, we measure up to a 12.6% higher RDMA read latency. This performance impact was actually overlooked by previous RNIC offloading studies. To solve the first challenge, we propose a technique called QP and memory window grouping. The key observation here is that different memory windows can actually be bound to overlapping memory areas. So instead of binding one memory window per chunk, we pre-allocate a group of memory windows for each chunk. We also organize QP connections on the compute node side into QP groups with the same number of QPs as memory windows in each group. During allocation, the work request chain binds each memory window in the group to the same memory chunk and aligns each memory window to a different QP in the compute node's specified QP group. Now the compute node can access the same memory chunk through any QP in the QP group. Each QP in the QP group provides a distinct access path for the compute node. This can eliminate the performance interference. For the second challenge, we propose management access QP separation. The key observation here is that allocation operations as a control path operation happen much less frequently than access operations. So instead of giving every QP its own offloaded logic, we designate a small number of dedicated allo QPs and free QPs to handle memory allocation and deallocation requests. Only these QPs contain the offloaded work request chains. For memory window assignment, we deep dived into the RNIC driver and found that the RDMA bound memory window work request actually contains a QP in field. The allow QP can perform memory window binding operation while assigning the bound memory window to access QPs by simply setting the QP in field to the target access QP's QPN. So in the evaluation, to demonstrate the effectiveness and efficiency of one-sided memory window, we evaluate the system in a cluster with 6 compute nodes and 1 memory node, each with 100 Gbps Connect X5 RNIC. The memory node uses only one CPU core to simulate its weak processing power. We compare one-sided memory window against 3 baselines: static MR, RPC memory window, and ODP. We first integrate one-sided memory window with wrist hashing, a state-of-the-art disaggregated key-value store. The memory nodes divides memory into fine-grained chunks, and each compute node requests memory chunks and organize them into size classes to minimal internal fragmentation. Here are the results for an insert-only workload with 1 KB key-value size, followed by randomly deleting 90% of the inserted pairs. ODP is not included in this test since it's a kernel swap-based system. The x-axis shows the number of compute node threads. The y-axis shows throughput, P99 tail latency, and peak memory node CPU usage. As we can see in the figure, RPC memory window scales poorly due to the memory node CPU becomes a bottleneck. At 288 threads across 6 compute nodes, it achieves only 6% of static MR's peak throughput. At the same allocation granularity, one-sided memory window can achieve up to 10.6 times higher throughput than RPC memory window. Compared to static MR, which use coarse-grained allocation, one-sided memory window with 8 KB allocation granularity can save 43% of memory after random deleting 90% of key-value pairs, while introducing at most 19.8% performance overhead. We also integrate one-sided memory window with fast swap, a state-of-the-art kernel swap-based disaggregated memory system. The memory node partitions memory into 1 MB chunks, which in practice can provide a substantial improvement over static allocation. And each compute node divides its swap space into 1 MB segments and maps them to remote memory on demand. Running real-world cloud applications, including k-means, memcached, and 2 graph processing algorithms, one-sided memory window introduces at most 3.8% performance overhead. Compared to static MR, ODP can achieve up to 2.4 times higher memory utilization. Compared to RPC memory window, one-sided memory window delivers a 19.7% performance improvement. Compared to ODP, one-sided memory window delivers a significant 25.8% performance improvement. This demonstrates the efficiency of one-sided memory window in balancing memory allocation granularity with performance. So to conclude, one-sided memory window combines RNIC offloading with type 2 memory window to build an efficient one-sided remote memory allocation primitive for DM systems. We use type 2 memory window for strong isolation and propose two novel techniques, QP and memory window grouping and management access QP separation to solve the performance challenges introduced by type 2 memory windows. The result is a system that achieves high memory utilization, high allocation and access performance, zero memory node CPU involvement, arbitrary I/O granularity, and strong isolation. More details, including the full security analysis, are in the paper. Thank you all for listening, and I'm happy to take any questions.